Good evening, class. Here's exam 2 review, covering chapter 3, differentiation rules. So from 3.1 to 3.8, and the first part covers from 3.1 to 3.3. So we're going to cover derivatives of polynomial and exponential functions, the product and quotient rules, derivative of trigonometric functions. There's a pledge I'm going to remind you. When we take the exam, we pledge not to receive any unauthorized assistance. Unauthorized actions include but are not limited to the use of notes, text, graphing calculators, search engines, PowerPoints, AI, or any other resources not explicitly allowed. All right, so differentiation. Let's start with the definition. dy dx is the limit of delta y over delta x as delta x approaches 0, or f prime of x equals limit of f of x plus h minus f of x over h as h approaches 0. Now, the derivative of a constant is 0. The derivative of x to the power of n is nx to the power of n minus 1. This is known as a power rule. The derivative of k times x is k, where k is a number, is just a coefficient of x. And exponentials e to the power of x, the answer is itself. The derivative of x as a result of this power rule becomes 1. The derivative of c times f of x, you can take the c out, and the derivative of the sum is the sum of the derivatives, and the derivative of the difference is the difference of the derivatives. Definition of E is equal to the limit of 1 plus 1 over n to the power of n as n approaches infinity, or E is such a number that the limit of e to the power of h minus 1 over h as h approaches 0 equals 1. The derivative of sine is cosine. The derivative of cosine is negative sine. And over here, I want to mention just two of them. This is the shorthand notation for the product rule, and this is for the quotient rule. Fg prime is f prime g plus g prime f, and f over g prime is f prime g minus g prime f over g squared. In other words, now we are going to go with the easy way out. So up to now, definitions, and now we are going to go with the easy way out. For example, right here, we want to differentiate y equals x to the power of 1000. And we're going to go with the power rule. According to the power rule, the exponent becomes the coefficient, and then it goes down by 1. So 1000 x to the power of 1000 minus 1 is 999. Y equals 3r squared. If you want to differentiate this, number 3 remains, and you work with r squared. So 2r to the power of 2 minus 1. In other words, y prime or dy dr or ddr of 3r squared equals 6r. It's important to know the Leibniz's notation tells you exactly what is the independent variable, in this case, r. Now, as far as this polynomial is concerned, to differentiate, we're going to do it term by term, starting with the first one. 8 sits in front, and the exponent goes down by 1. So we have 8x to the power of 7. So f prime of x starts with the first one, 8x to the power of 7. This one, 12 times 5, 60x to the power of 4, so plus 60x to the power of 4. This one, negative 4 times 4, negative 16x cubed. This one, you multiply these two, plus 30x to the power of 3 minus 1, x squared. Minus 6x, the derivative of kx is k, minus 6, and 5, any constant, the derivative is 0, so minus 6, and we are done. So basically, we are using the differentiation rules. Extremely simple. F of x is x times square root of x plus 5 minus 2. To differentiate this, we are going to use some algebraic techniques first. And we're going to write square root of x as x to the power of 1/2. Then we notice this has exponent 1. And the product of these two, we use the product rule. A to the power of m times a to the power of n is a to the power of m plus n. So this becomes x to the power of 1 plus 1/2, which is 3/2, 5x minus 2. We do that so it becomes ready for the next step, which is simply differentiation using the rules that have been discussed. So what happens here? 3/2 x to the power of, subtract 1 is 1/2, plus 5. And of course, x to the power of 1/2, we know it's square root of x. We put it back in the same format. F of x is 2, x to the power of 5 over 9, x to the power of 9. Again, we are going to use one of the exponential rules, more specifically the quotient rule. And this becomes x to the power of 5 minus 9. So 2 over 9 x to the power of minus 4 is the elementary algebra. And now, to differentiate 2 over 9 remains times negative 4 x to the power of subtract 1 minus 5 or minus 4 minus 1. As you can see, this is minus 8 over 9, right? X to the power of minus 5 goes down and it becomes x to the power of 5. And I'm looking at negative exponential rules indicating that if you have a negative exponent, just move it. If it's down, bring it up. If it's up, bring it down and change it to a positive. What is the derivative of pi squared? What is the derivative of e? What is the derivative of 5? What is the derivative of any number? It's 0. Understand pi squared is a number, is a constant, therefore the answer is 0. And that's the key. What about this case? We are going to rewrite this using the nth root of a to the power of m. So it becomes 2x to the power of 4 over 5, being able to go back and forth, putting it in a format such that the power rule can be used. So 2 times 4 over 5, x to the power of 4 over 5 minus 1. So we have eight over 5, x to the power of 4 over 5 minus 1, negative 1 over 5. We take this down, we make it x to the power of positive 1 over 5 or the fifth root of x. So the final answer, the same format, f prime of x becomes 8 over 5, the fifth root of x. It's important to have the proper format. It's a warm-up example for the product rule. We are going to differentiate and not simplify. Needless to say, it must be simplified for the final answer, so you're going to finish that one. What I want to explain is this. Obviously, you can distribute and then use the power rule, but this is just for the sake of showing how the product rule works. The shorthand notation I use for product rule, fg prime, that means f of x times g of x, take the derivative prime, is f prime g plus g prime f. Those of you who already know that, you may have it in a different order. Remember the commutative property of addition and multiplication, you can put them in any order you want. So for example, this may be fg prime and first, okay? But the reason I'm going with that, because for the quotient rule makes it easier to memorize. So the product rule is f prime g plus g prime f. The quotient rule use the same thing with the negative in between f prime g minus g prime f over g squared. So it makes it very easy to memorize that, in my opinion. So having said that, this is the f function. The other one is the g function. We're going to go with that and take it from there. So now, according to this, f prime becomes 4x cubed minus 6x squared times g, the blue function, plus g prime is simply 6x minus 5 times f, the red function. And bear in mind, this is not finished. I expect you to finish it at home. But the purpose of that to mention the following. The most important step is the calculus step, and this is the only calculus step. What is left is just a bunch of algebraic steps. Having said that, let's look at another warm-up example. Y equals x squared sine x. We should recognize this as a product of x squared and sine x. Therefore, I put a raised dot in between to emphasize that. Therefore, I'm going to call one of them f, one of them g. So I'm going to use the product rule, f prime g plus g prime f. So we are using that. F prime is 2x times g, which is sine x, plus g prime, the derivative of sine is cosine x, times f, x squared, and we are going to rewrite it by putting the x squared in front. The final answer, y prime, is 2x sine x plus x squared cosine x. The reason we put the x squared in front, I don't want anybody to be under the assumption this is cosine of x cubed. So it's important to it in this manner. If h of x is x e to the power of x, find h prime of x. Well, we notice this is the product of x and e to the power of x. We put a raised dot in between. We call it f times g, and we're going to go with the product rule again. Again, we have memorized all these rules. So the way I would approach that, I would write the rule from the memory, and I would follow that. And what I'm mentioning in essence is that instead of writing d dx of this, d dx of that, because some of you have done this before, this is a lot easier and faster. So write the formula and just follow. Having said that, first I need f prime, which is simply 1, times g, which is e to the power of x, plus g prime, the derivative of exponential is itself, the derivative of e to the power of x is e to the power of x, times f, which is x. And I'm going to factor the e to the power of x out, and I'm going to write it e to the power of x times 1 plus x, or x plus 1 makes no difference. Find h double prime of x. So what is that? Higher order derivatives of f of x. The derivative of a function y equals f of x is itself a function. y prime equals f prime of x. Therefore, you can take the derivative of f prime of x referred to as the second derivative of f of x, f double prime of x, or f superscript 2x. It's important it's not the exponent of x. This differentiation process can be continued to find the third, fourth, and successive derivatives of f of x, known as higher order derivatives of f of x. Because prime notation becomes cumbersome, for higher orders, we use the superscript notation f, and then in the parentheses n of x to denote the nth derivative of f of x. In other words, I can say f prime, f double prime, f triple prime, and then it becomes, awkward. So that's why we use that for higher. In any event, now I'm going to take the derivative of this one to get h double prime. So this is a product of f and g. So I'm going to call this one f and this one g, and go with, again, the product rule. F prime is itself e to the power of x times g is the parentheses 1 plus x, x plus 1 makes no difference. And then plus g prime, the derivative of 1 plus x is simply 1 times f, which is e to the power of x. And I hope you see that we have e to the power of x times x plus 1 plus 1, which means x plus 2. And that's the final answer. H of t is the fourth root of t minus 4e to the power of t minus cosine t over 2. We want to differentiate. First, we have to put this in a format. Let me erase my work. We have to put this in a format such that differentiation is easy. So we're going to write a t to the power of 1/4. This one you don't have to, but rewrite it as negative 1/2 cosine t in case. I want to make sure everybody can see that you really are dealing with cosine. Negative 1/2 is just a coefficient. So starting with this, h prime of t equals this one, 1/4, t to the power of 1/4 minus 1. This one is itself, minus 4e to the power of t. This one, negative 1/2 times cosine, the derivative is negative sine, times negative sine t. So this is negative 3/4. You take this down, make it t to the power of positive 3/4, or the fourth root of t cubed. So 1/4, fourth root of t cubed, this doesn't change. This one and this one, plus 1/2 sine t, or plus sine t over 2. I put it in this format just to have the same format we receive. Not that it matters. Find the limit. The limit of sine 3x times sine 5x over x squared as x approaches 0. And you can see in the lecture that we've proved the limit of sine theta over theta as theta approaches 0 is 1. The limit of cosine theta minus 1 over theta as theta approaches 0 equals 0. So what is the methodology? The methodology is to make sure this looks like one of those. In the numerator, we have sine, we have two of them. So we're going to cut it into two pieces. Sine of this times sine of that. Okay. And the denominator, we're going to call it x and x. In other words, we have the limit as x approaches 0, sine of 3x over x times sine of 5x over x. Now, it's important to understand what this tells us. If the argument of sine, and by the way, the argument of sine you can't change, is whatever, in this case, theta, and it's identical to the denominator, and that argument approaches 0, then this will result in what? In other words, this you can't change this. 3x, okay? So if this were 3x and this was 3x, this would be 1. Since this is sine of 5x, if this was 5x and this was 5x, this would be 1. So what is the methodology? It's very simple. This one, number 3, is missing. So I'm going to multiply this fraction by 3 over 3, and this one I'm going to multiply it by 5 over 5. This one 3 by 3 because this is sine of 3x. I want to make this one 3x. And in other words, I'm looking at this part. The next one I'm going to do 5, and I'm looking at this part. Okay. Now, I'm going to take the 3 out for this one, and I'm going to take the 5 out for this one, and I'm going to use the limit clause and write 2 up. In fact, x is approaching 0. Why did I change it to 3x? X is approaching 0. Why did I change it to 5x? Note, as x approaches 0, 3x approaches 0, 5x approaches 0. You have to show that. Therefore, because this one and this one and this one are identical, this is 1. This one and this one and this one are identical, this is 1. So the answer is 3 times 5 equals 15. Or in the first case, let me just erase again my work. In the first case, you can let 3x be theta. In this case, you can let 5x be gamma or theta or alpha or even the same theta is fine. All right. The limit of cosine theta minus 1 over sine theta as theta approaches 0. Obviously, we don't have any of this, but we can use our algebraic techniques to make it look like that. In this case, we notice we can divide the top and the bottom by theta. By the way, theta is not 0. Theta is approaching 0. Otherwise, you can't divide by it. And now, according to the limit laws, I can make up 2 limits, the limit for the top, the limit for the bottom, and each case follows this one. So this is 0, this is 1, 0 over 1. The answer is 0. So you want to make it look like that. Again, I want to mention here later on we learn other methods. For example, some of you have heard of L'Hopital's rule. Not now, we cannot use it, but later, as we go over L'Hopital's rule, then you can use it. For now, we are going to approach such that these 2 theorems can be used. Limit of cosecant x, sine of sine x as x approaches 0. We know cosecant is 1 over sine. So we can replace this with 1 over sine. And now it's important to know that I made a change here. X approaches 0, not sine x. How did I make a change? I have to explain. Note, x approaches 0, also sine x approaches 0. Okay? Because sine of 0 is 0. So one easy way to understand this, let theta represent sine x. So anywhere you see sine x, change it to theta. And this becomes exactly what we have here. And the answer is 1. I mean, if right from here to you come up with the answer 1, I'm okay with that, but I just want to make sure that it's completely justified. To do this, let me erase my work. The limit of sine x squared over x as x approaches 0. When we go back to this, it's important to know that the argument of sine, argument of any trigonometric functions cannot be touched. So you can't change that. But you can manipulate this. How? You can say, okay, if it were x squared, we would be in good shape. So let's multiply this by x. So if you're multiplying this by x, that means you're multiplying the denominator by x. So let's multiply the numerator by x also. Now, you take the x out, and you take the limit of x as x approaches 0 and limit of the rest of it, which is sine x squared over x squared. as x approaches 0. So let me make sure we understand what happened here. This one, limit of x as x approaches 0. The rest of it, limit of sine x squared over x squared as x squared approaches 0. Why? Well, note, when x approaches 0, x squared approaches 0 too, because they must be identical. Notice, this one and this one and this one must be identical for it to be 1. You don't have to change it to theta anymore. So this thing now goes to 1. But the first one goes to 0. Their product is 0. Quotient rule. Here's a warm-up example. And we're not going to simplify it here. So f over g, I would write this from the memory, f prime g minus g prime f over g squared. So I'm going to call it f over g. The numerator is f, the denominator is g. So f prime 4x cubed minus 6x squared. And this is 0. So 4x cubed minus 6x squared times g. Just write the bottom, the blue function, 3x squared minus 5x, minus g prime 6x minus 5 times f, the top function, x to the power 4 minus 2x cubed minus 7, over, just write the denominator in a parentheses and square it. You want g squared. And of course, I expect you to finish it. It's important to know in some instances, this may be acceptable as a final answer by your digital platform. Not for the exam, not acceptable. You have to finish it. What about this one? F of x is 10x squared minus 7x cubed over x squared. The question is, do I need a quotient rule? And that's important to understand. If you need a quotient rule and you try to avoid it, normally you make it more difficult. On the other hand, if you don't need it and use the quotient rule, you make it even worse. So notice, your algebraic techniques tells you this fraction gives you 10, this one gives you minus 7x, and simply put f prime is minus 7. So in a split second, you come up with the answer as long as you use your algebraic techniques properly. Y equals 1 plus sine x over x plus cosine x. We want to differentiate that. And to do so, we notice you have to use the quotient rule. We're going to call it f over g. So let me box. This is the one we're going to use. F prime g minus g prime f over g squared. So f prime, the derivative of 1 is 0, sine is cosine x. Times g, just put the denominator x plus cosine g, x plus cosine x here. Minus g prime 1 plus the derivative of cosine is negative sine. So 1 minus sine x times f times the top 1 plus sine x over g squared. Just write the bottom in a parenthesis and square. And I'm going to write this is f prime g minus g prime f over g squared. I'm going to erase it in a moment. Just I want you to see this shorthand notation really helps. So we want to distribute, and This is x cosine x. This is cosine squared. What about this one? A minus b, a plus b. It's a squared minus b squared. So minus 1 minus sine squared. Of course, the denominator, we don't touch it. So what is 1 minus sine squared? I'm going to remind you of some Pythagorean identities we've learned in trigonometry or pre-calculus. Sine squared plus cosine squared is 1. Tan squared plus 1 is secant squared. 1 plus cotangent squared is cosecant squared. So if sine squared plus cosine squared is 1, then cosine squared is 1 minus sine squared, and sine squared is 1 minus cosine squared. So 1 minus sine squared can be replaced by cosine squared. We can cancel these two, and the numerator is just x cosine x. The final answer y prime is x cosine x over the parentheses x plus cosine x quantity squared, and we are done. Derivative of trigonometric functions. So let's go over them. The derivative of sine x is cosine x. The derivative of cosine x is minus sine x. And the proof for this one, it uses those limits that were mentioned in the beginning. The limit of sine theta over theta as theta approaches 0 is 1. We have gone over that. And the limit of cosine theta minus 1 over theta as theta approaches 0 is equal to 0. We use those, and you can find them in the lecture. But what about tan x, for example? The derivative of tan x is secant squared. The derivative of cotangent x is minus cosine. Cosecant squared. The derivative of secant x is secant x times tan x. The derivative of cosecant x is minus cosecant x cotangent x. Well, we are interested in finding the derivative of tan x. We want to prove it's secant squared. So we're going to write the tan x as sine x over cosine x. And I'm going to remind you of reciprocal identities. Tan x is 1 over cotangent x. Cotangent is 1 over tan x. Secant is 1 over cosine. Cosecant is 1 over sine. Those are called reciprocal identities. Also, tan x is sine over cosine. Cotangent is cosine over sine. So we use one of those because we have the information about sine and cosine. We are going to go with sine and cosine. And obviously, f over g, we are going to use the quotient. F prime g minus g prime f over g squared. So f prime, the derivative of sine is simply cosine, times g, which is cosine, minus g prime, the derivative of cosine is negative sine, times f, the numerator is sine x. Over g squared, cosine squared. So this is cosine squared plus sine squared, everybody, which means it's 1 over cosine squared. If 1 over cosine is secant, then 1 over cosine squared must be secant squared. So we proved the derivative of d dx of tan x is secant squared x. We continue with the thoughts of derivatives of trigonometric functions. We want to prove d dx of secant x is secant x tan x. Reminding you of all of those, we should know, and again, I'm going to repeat, the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tan x is secant squared. Cotangent is negative cosecant squared. For secant, we get secant x tan x. For cosecant, minus cosecant x, cotangent x, and there are a bunch of trigonometric identities. Hopefully, everybody remembers. If you don't, hopefully it's coming back to you. So having said that, we are going to deal with secant x, and so we let y or f of x be secant x, and we choose it, of course, in this format, 1 over cosine, because we know how to deal with cosine. And we notice that this is also f over g, and we have to use the quotient. F prime g minus g prime f over g squared. F prime, any number, the result is 0, times g cosine x, minus g prime minus the derivative of cosine is negative sine x, times f times 1, and just write the bottom and square it, cosine squared. Obviously, this is 0. This is negative times negative positive sine x. So we end up with sine x over cosine squared x. And as you recall, when we wanted to prove identities in trigonometry, we would uh, use various techniques and use previous identities. So because we want it to look like that, we are going to cut it into two fractions, 1 over cosine times sine over cosine. 1 over cosine is secant x, sine over cosine is tan x, and believe it or not, we just proved d dx of secant x is secant x tan x. Just as we did in trigonometry, we use previous information to prove new information. In the case of trigonometry, new identities. Y equals 1 minus secant x over tan x. To differentiate this again, we notice it's a fractional form, f over g and it requires the quotient rule. So I'm going to write the quotient rule from the memory. I can't emphasize this enough, everybody. And I'm going to apply that. It's a good practice to do so. All right, so we need f prime. The numerator 1 gives you 0 minus, you keep the negative sign. Secant gives you secant x tan x. So minus secant x tan x times g times tan x. Minus g prime f, g prime, the derivative of tan. So minus the derivative of tan x is secant squared x. Times f, just write the numerator in a parentheses 1 minus secant x. Then what about the bottom? Just write it and square it, tan squared x. And I'm going to put an asterisk next to it, meaning this, believe it or not, is the only calculus step. But of course, it's not finished. So we're going to finish that. So to do so, we have negative secant x tan squared minus secant squared x plus secant cubed x, the denominator remains unchanged. And we notice in the numerator, we have a common factor. All of them have a common factor of secant x. I can take out the common factor of secant x. If I do so, I get negative tan squared minus secant x plus secant squared x, and the bottom doesn't change. So I'm just factoring the secant x minus tan squared x minus secant x plus secant squared x. Now, we looked at Pythagorean identities in trigonometry, and one of them was 1 plus tan squared is secant squared, which means if I move the tan squared to the right, 1 equals tan squared, 1 equals secant squared minus tan squared. So I'm going to move this to the right. Secant squared minus tan squared, secant squared minus tan squared equals 1. So I can replace these two according to Pythagorean identity. I can change them into 1. So the final answer becomes secant x, and the brackets becomes 1 minus secant x, this one remains, over tan squared x. This is the final answer. Find the points for which the tangent lines are horizontal. So we have two things here, tangent lines and then horizontal. In order to get to slope of tangent lines, we have to differentiate. So if I differentiate, f prime of x becomes 3x squared minus 6x. And for any line to be horizontal, its slope must be 0. So tangent lines, their slopes in general is that, and of course you have to have a specific point, and then you plug in, you calculate the slope for that point. To be horizontal must be equal to 0. I hope we understand where this 0 comes from. The slope of any horizontal line is 0. So to solve this, we're going to factor out the 3x. We get 3x times x minus 2. And x is either 0 or 2. And by the way, it doesn't matter that you have 3 here or 3,000 or negative 1/2 makes no difference. It's just a coefficient. X is 0, x is 2. Now, it's important to know those represent two different points. So if I plug in 0 here, I hope you see that I get 0, 5. If I put 2 here, because I want to get the y coordinate, I get 2 cubed, which is 8, minus 3 times 2 squared, 2 squared, 4 times 3, 12, so minus 12, and then plus 5. So 8 minus 12 plus 5 is just 1, and the second point has coordinates to 1. It's important to understand. I don't want anybody to be under the assumption this means 0, 2. That's not what it means. X is 0, find the y, you put it into the original function. X is 2, find the y, put it into the original function. There are two pairs, 0, 5, 2, 5. Okay, those are the points where tangent lines are horizontal.